speaker is from Imagination, and he's David Hough. He's a distinguished systems architect at Imagination. His team developed the company's the previous generation and the current new generation of neural network accelerators that he'll be presenting to us today. So welcome, David, and you can go ahead and share your screen.
Hiya. So hello, everyone. I'm David Hough from Imagination Technologies. So today I'm going to talk a bit about our upcoming AI inference IP and how the architecture for it can scale to different performance points, including all the way up to 100 terops of performance. So just as a quick overview of the talk, I'll talk a bit about how the workloads people need to run are evolving, the challenges that brings, and what goals we need to target to allow SoC developers to address these challenges. Then I'll talk a bit about our upcoming architecture and how it can help. Dive a bit into our tiling algorithm that is used by the design, and finally give a very brief introduction to our software stack so you have some idea of how it all fits together. So to start, the challenge, really, or the challenges. Now, one of the main ones is obviously that there's an ever-increasing demand for processing power for neural networks. And that's being driven by a number of trends. Some of it is simply just bigger networks, but that's not necessarily just in terms of the number of weights or the parameters within the network, but it's also in terms of the size of the input data that you need to process. I mean, for vision-related use cases, for instance, processing high-definition video obviously requires that little bit more performance than just processing low-resolution images or anything like that. But it's also being driven by workloads requiring multiple different networks to be run. You're not necessarily just trying to do one thing on one piece of input data, but potentially many things on that input data, or many things on many different bits of input data. But of course, the world is never quite that simple, as none of that means that the lower end is actually going away as such. Rather, it's just that there's an expanding range of performance points needed for different edge processing use cases. And particularly at the edge, you still have a need for the smaller, lower power devices that are targeting specific use cases. If you're just doing real-time speech recognition, for instance, you're unlikely to need all the way up to 100 terops of performance. So there's a number of different challenges raised by all of this, particularly in how we as an IP vendor can build designs that can scale to address that wide range of workloads, but also to how to cope in a design with all those different workloads potentially at the same time, potentially needing quite widely different performance characteristics. Now, if we take a bit of a high-end example, we can look at all the many different sensors on a car, and you can quickly see that not only do you have many sensors, but the data from those is used for many different things. So you quickly get into the case of quite a few different models and workloads that you need to run, with potentially multiple workloads or multiple networks being run on the same input data, or you're running at the output from one network as the input to another network, and so on. So you get many different things going on, and they can all have different performance needs and characteristics. We say different sensor sizes, different processing rates coming in, different networks complexities, and so on. And indeed, if you look a bit more at the kind of performance needed and the input resolutions for a number of different use cases in that space, you can quickly see that the demand and requirements are going up as more functionality is added, but there's still a wide range of potential cases to address. So given all of that, what are the goals we need to design our IP around? Well, what we're aiming for with our new generation of IP is to come up with an architecture that can scale, essentially, both in terms of being able to scale up to much higher performance points, where in this case we're aiming to get all the way up to 100 terops, but also being able to address the performance points in between for whatever designs or use cases our customers end up needing. And it's also worth bearing in mind, particularly at the edge, performance doesn't just mean throughput. It's also very important what the latency of processing an individual input is. And of course, when it comes to increasing the performance in particular, one of the bigger problems we need to tackle is keeping that amount of memory bandwidth that we use from the rest of the system in check, as that can obviously quickly become a significant problem as you increase performance. And all the while balancing all of that against the cost of the silicon area and the power and so on. So how have we tackled all this? Well, we've taken a multi-core approach to the architecture. It's a configurable design where we can change various aspects, including the number of cores and the sizes of the various local memories to keep data local. That allows us to scale relatively easily to different performance points, while balancing that with whatever bandwidth and silicon area targets different customers or use cases may have. At the high end, that allows us to scale up all the way to 8 cores, each of which is capable of 4,096 max per clock. And as we design the IP to be able to get clocked up to 1.5 gigahertz in 7nm technologies, all in, that means you can get up to about 100 teraops of performance. But for smaller performance points, we can, of course, take that all the way down to 1 core, or any number of cores in between, depending on the use case. Also, as you can hopefully see from the diagram, each of the cores has what's marked as OCM, or on-chip memory, as we refer to it, which is really just dedicated SRAM, to store data local to each individual core. Then there's a single shared on-chip memory, or SRAM, that all of the cores can access via an internal interconnect to share data, to help share data between them. And as I mentioned, that total memory size is itself also configurable to give some flexibility in the trade-offs our customers may need to make between silicon area and the amount of external memory bandwidth that is consumed for a particular inference. And while you may notice from the slide that the configurability is quite large amounts of SRAM, our recommended sizes are typically much smaller than that. The upper limit is more about making sure the flexibility is there just in case, rather than we expect most customers to need quite that much. Now, an important point to highlight here is that although this is a multi-core design, we are splitting a single inference across all the cores. There is no requirement to batch up multiple inputs in order to make use of all the cores. They can all work together on the same input. Now, if we look at one of the individual cores within the system, it's got a configurable compute pipeline made up of a number of different units for different types of operations, where the bulk of the compute is located in what we refer to as the convolution engine. That supports convolutions, obviously, and similar MAC-based operations, and can perform up to 4,096 max per clock when using 8-bit integer precision. We also support up to 16-bit integer precision if you need it, and that's throughout the pipeline, but that's a slightly lower throughput. Now, the data that's generated by the convolution engine is then streamed through the pipeline to other blocks, allowing a group of different network layers to essentially be executed in parallel. And it also allows the compute time of the non-convolutional layers to essentially be hidden, as all the other blocks are designed to keep up with the maximum output rate from the convolution engine, as well as that pipelining, avoiding any bandwidth costs for that intermediate data between those layers within the same group. And as you can see from the slide, an example of such a group of layers, or layer group, as we refer to it, could be a convolution operation, followed by an activation, followed by a residual add, followed by a building operation, for instance. And where, in that case, only the input to the convolution would be read from memory and the output of the pooling would be written to memory. Now, I mentioned just now that we split a single execution across multiple cores, and also that we want to keep our external memory bandwidth low. Now, our tiling approach is one part of addressing both of those problems at essentially the same time. But before I dive too quickly into that, for anyone not already familiar, or as a brief reminder for others, I just want to give a bit more context about what's actually going on when we talk about tensors and running a network and so on. So primarily what we're really talking about is a sequence of operations, such as convolution or activation, that take in and output a multi-dimensional array of elements, or a tensor. And in the simplified example on the slide, we're looking at a 3-dimensional tensor, which can be thought as having 2 spatial dimensions, a width and height, and a depth dimension. And to calculate each individual output element, an operation such as convolution only selects a small sliding window of data from its input in many cases. Now, obviously, there's a lot more that can be said on this topic, but for now, the main thing we want to take away here is that for most operations, there is only that small window of input data that's needed to calculate any individual output value. Now, why is that particular takeaway important? Well, the very basic high-level idea here for our tiling is that we can use that fact to split the input data into multiple independent tiles in the spatial dimension. We can then process just an individual tile to generate a single tile of output for a particular operation. That output tile can then become the input tile for the next operation, and so on, allowing us to execute a single small tile across a sequence of potentially many layers before going back and selecting the next tile to execute across all of those layers. Now, why would you want to do that? Well, it means the amount of intermediate data that needed to be stored between each of those layers was only ever as big as an individual tile, rather than needing to store the entire tensor. So it's potentially much easier to fit in a local memory rather than having to write it back to external memory. And as I mentioned earlier, one of the things that's driving the need for more compute power is that larger larger input resolutions. So those intermediate tensors are getting bigger and bigger as the workloads evolve. Now, on the slide, the diagram at the top is showing a sequence of tensors generated by an example network, where it's not using tiling or local memory, and in that case, the complete tensors need to go back and forth to external memory after each layer. Whereas the diagram at the bottom is trying to show the same example, but this time using tiling. The input is split into two tiles, and then the network itself is split into two tile groups. Within an individual tile group, we can execute, say, tile 0 across all the layers within that tile group before coming back and executing tile 1 across all those layers. And within that, all the intermediate data just needs to go back and forth to our local on-chip memory, with data only really needing to touch external memory between those tile groups. So we can effectively end up being able to execute large parts of the network without actually needing to touch external memory at all. Of course, the other thing to bear in mind here is that in order to execute tile across those multiple layers, we didn't just need the input data, the intermediate data to be stored locally, but we also needed all the parameters for those layers as well. So there are various trade-offs that the compiler needs to consider when selecting the tile sizes and which layers to group together into the same tile groups to make sure that everything fits in local memory. And when we take all of that as a whole, that effectively gives us an approach where what can be thought of as the working set size can be adjusted to have a much local memory that the design is configured with. And finally, that also gives us the potential for a handy way to distribute a network across multiple cores by simply having each core work on a different tile. Now, this is a bit more of a complicated example. In this case, it was for an internal ResNet style network. But on the slide, each small block corresponds to a group of layers that can be executed together in the core compute pipeline I mentioned earlier. And as you can hopefully see, this network graph has a number of complications for any real-world tiling implementation, including cases where the output tile is used by multiple operations later in the network, and cases where multiple inputs are needed for a particular operation. And that sort of complication can expose some interesting constraints. As for instance, the multiple different layer operations might need slightly different tile sizes, or you may need to have things like multiple intermediate tiles at the same time, corresponding to different branches of the graph, and so on. But currently, all the blocks are marked as red on the slide, and that corresponds to their output data needing to go to external memory. But once we apply tiling, you can hopefully see that most of them disappear, or become white, corresponding to their output being stored in local memory instead, significantly reducing the external memory bandwidth used. And on the slide, the boxes around the various columns correspond to the tile groups that were selected by the compiler. So you can see that only the data that is output from a particular tile group needs to go to memory. Now, obviously, the actual impact for any of your individual networks out there that you need will vary based on the network and the SRAM sizes. But essentially, that variation will be more or less of these blocks becoming white or red, or going to memory or going to local memory instead. And with a small enough network or a big enough RAM, it can be as simple as the entire network is a single tile group. And in that case, only the final output would need to be written to external memory. Now, for multi-core, as I said, one of the main ways we distribute the work across cores is to give them each a different tile to process. And in that case, where the compiler would need to select tile sizes to make sure they distribute evenly across a number of cores. And once we've done that, that gives us a nice big independent chunk of work for each of them to do. And means there's only a fairly coarse-grained synchronization that's actually required between them. However, there is one complication that I haven't touched on yet, and that is the tiles of the input data themselves can overlap, where, say, the last bit of input data needed for tile 1 is also needed as the first bit of input tile for tile 2. And that typically corresponds to where a particular operation needs a window of input data that would otherwise cross the tile boundary. Now, there's a couple of ways you can handle that. you could have each core recompute that intermediate edge itself, for instance. Or in our case, we share that edge data between the cores, trying to show in the first diagram. There, most of the data is kept local, the red arrows, but some data written by the first core is then shared by both cores on the next layer, and that's what the black arrows are trying to show. And of course, moving beyond that, there are also other networks where with smaller tensor sizes, for instance, or other types of operation that don't really lend themselves to tiling. So it doesn't apply to literally everything. And particularly when you split into many cores, there's only so many ways you could split, let's say, a 2x2 tensor or 1x1 or whatever. And in those cases, we need other approaches to splitting it. And the bottom diagram is showing an example of splitting in the channel dimension or the depth dimension instead. So how well does all of this actually work in practice? The chart on the left shows how the multicore performance scales as we increase the number of cores for a couple of fairly simple benchmarks. And it's showing that for networks that, can show that for networks that tile really well, the scalability also scales very well with very little overhead. And that corresponds to the SSD ResNet 34 benchmark, or the red line on the slide, which had an input, in this case, had an input resolution of 2400 by 1200. Then for networks and layers with smaller tensors that don't always split as well into tiles, particularly if you need to split it across many cores, you still get good scaling, but there's a bit more overhead. But that corresponds to the purple line, or the ResNet 50 benchmark, which is just using a 224 by 224 input. And just to add at this point, all of these results are with a batch size of 1. So that improved performance you're seeing there with more cores directly corresponds to reduced latency for a single inference. Now, on the right, we can see how the external memory bandwidth can be reduced by just adding a relatively small amount of on-chip memory. And of course, if your silicon area budget allows you to increase the SRAM sizes, that external memory bandwidth can be reduced much further. Now, the multicore approach itself also has some other interesting benefits, particularly when it comes to handling multiple workloads, as we can now support different workloads on different cores running in parallel. That gives us multiple options for how to schedule that different work, potentially giving quite fine-grained control to whoever's using the system. Obviously, the simplest approach is just to always split every network across all cores and then just only run one network at once. But we also have some other options, which diagrams on the right are trying to show. Firstly, you could reserve an individual core or multiple cores or groups of cores for particular workloads, so that they're not interfered with by whatever else, what's running on in the other cores. And there's also another option of being a bit more dynamic, where the multi-core system can be switched between different subdivisions over time. Where the second diagram is trying to show that is allow you, for instance, to run a single network across all the cores, then switch to running a network across only 2 cores, while running the other networks, or running 2 other networks on 2 other cores, for instance, or any other combination you might want at any particular point in time. And essentially, you have fine-grained control over the various latency versus throughput trade-offs that you might actually have in your real-world systems. And finally, I'll quickly just give a quick talk about our software stack so that you can see how it might actually fit in, and you might actually use it. So the software stack is an offline tooling to support either pre-quantized or floating point networks from various different frameworks, including TensorFlow, ONNX, and so on, and then compile that offline down to the accelerator. If it's not already quantized, we can also provide offline tooling to profile the network and quantize it via that profiling data. Once you've compiled it, we also have some offline tooling for estimating performance without actually having to run the network. And that can be particularly useful for evaluating different configurations or scheduling approaches before you actually get to silicon. Then at runtime, we have a common API that's shared with our GPUs for executing those pre-compiled networks. So I think that's about it. In quick summary, thinking back to our original design goals, we've come up with a configurable multi-core architecture that's scalable from 10 to 100 teraops of performance. And our tiling approach allows us to keep our external memory bandwidth and area in check somewhat with limited amounts of area required for local memories. So yeah, thanks for listening. And I guess over to any questions.
Okay, hi David, thanks for your presentation. We have a couple questions coming in. I thought you can go ahead and stop sharing your screen first.
Yeah.
I think maybe a little bit more detail if you could provide some on this tiling approach. It looked like you said that the compiler decides on the tile configurations. Could you say a little bit more about what that's based on?
Okay, yes. So yes, it would be the compiler makes those decisions when it at the compile time. So this is an offline decision, and then at runtime it's already predefined. It will be looking. So ideally, you want to group as many layers as possible into a tile group. However, the more layers you include in a tile group, the more parameters you need to store. Because if you're going to run a particular layer, a tile for a particular layer multiple times, you don't want to reload those parameters each time you rerun a separate tile. So the more layers you group together, the more RAM you have to allocate for those parameters, while at the same time you have to allocate space for the tiles themselves. And if you've got particular complex cases, as we were showing in more kind of the resonance style, where you've got multiple branches, you potentially have to store space for multiple tiles to different branches at the same time, and so on. So the compiler is essentially trying to trade off how many cores have I got, because I want to split that into multiple of that in terms of the number of tiles, but also how many layers I can fit together without overflowing my local memory. So it's essentially an optimization problem that can become quite complex depending on the structure of your network.
Sure. So it would seem that there's a balance necessary between the compute resources and the memory. Is the memory per compute core fixed, or is that also variable?
So once you've decided on a particular configuration in silicon, it will be fixed. But as we're providing IP, with our customers will have the option to select different sizes, and they can use, say, the offline performance model that I mentioned in the software stack to try out different options for those RAM sizes, and then say, okay, this works for our workloads.
Have you evaluated utilization? Does this improve hardware utilization?
In terms of performance, it can do. Most of it comes down to, are you bandwidth limited or not? If previously you were bandwidth limited, and now you're keeping all of the data local because you can fit this entire tile of data, and because you're just talking to that on-chip memory, you're not being limited by how quickly you can load data from say DDR, and in that way you're increasing your utilization. But directly in terms of compute, the tiling itself doesn't, although there are various other optimizations we've done in this generation of the design.
You haven't measured it to say 50%, 70% utilization that you get out of this approach?
I'm not sure I follow you in there. It certainly does improve it, and the utilization you would get
with a 4K Mac array, we've seen in the past that you're trying to adapt the convolutions to the size of the hardware, and sometimes you get poor utilization when you do that.
Hey, right. Okay. So yeah,
the tiling approach.
So the tiling approach itself doesn't affect the utilization of the convolution engines. I mean, once you've got the window of input data for your tile, you're then loading that directly into the cores, and the cores are just processing them as normal. So the utilization of the core comes down to yes, how well those convolutions map onto the Mac arrays, and we get reasonably good utilization out of that we've looked at on the previous designs, but this isn't changing that in this specific way in terms of scaling.
Let's look at some of the audience questions. How does sending the tiles of a larger image into the processing elements work when the initial image is larger than the tile size? Specifically, I think you may have discussed some of this convolution at the boundary of tiles.
So at the overlap, when you've got a very large tensor, you break it into a small amount of tiles. There will be some overlap for convolutions, yes. And in that case, if you think about single core for a short amount of time, you're going to execute a single core all the way through, and you're going to have a little bit at the bottom that's going to be needed by the next tile, which is that overlap. And in that case, we're also storing that overlap when we did the first execution, which is another bit of a memory we need to store. So when you come back and do the next one, that overlapping data is available in the internal memories, such that you don't need to recompute it again. And that's also what we're talking about in terms of the multi-core, where you're executing multiple tiles at the same time, where we're sharing data between the cores to cover that overlap.
We have a question on, does this tensor tiling approach only support convolution networks, or does it support other types of neural networks as well?
So it supports many different types of neural networks in terms of the design. As I said, some cases obviously don't tile that well.
And of course, this is licensable IP. Is it available for customer licensing now, or is a future date?
I'll actually pass that question over to Andrew Grant, who's also on the call. Andrew?
Yeah, hi, Mike. Good to see you again. Yeah, absolutely. It's available as licensable IP right away. We've been working with the tensor tiling stuff for quite some time now, and patents are applied for. And then we're already in beta and verification. So yeah, depending on the configuration that somebody's particularly interested in, then basically come and talk to us. We'd be delighted to discuss anybody's needs. And indeed, we're in the breakout session at 12, so we'd be pleased to talk to people then, with David as well, of course.
Sounds good. Great. Let's see, looking through the questions, I think you talked about this. You're duplicating the memory when you handle the tile overlap. You're storing the segment of the tile more than once. The other question is, in the convolution engine itself, is it essentially a systolic array, or is it something else?
No, it's directly optimized for convolutions. It's actually broken up into multiple smaller engines, each doing a subset of the max, and with an adder tree and so on to do the dot products involved.
And did you say what data types do you support for convolution?
So it's all integer. We support int8, and we also support up to 16-bit integer as well if you need it. And we support the common quantization schemes, such from like TensorFlow and so on.
Okay.
Mike,
let's see. I think we may have one more.
Yeah,
sorry, go ahead, Andrew.
Yeah, my apologies. And just as a follow-up to the question you just made, I should have added that we've already licensed the design already. So that's going into its first markets now, and obviously we're following up from that point. So we're already licensed into automotive.
Oh, great. There was a question on whether it's seen silicon yet, but it sounds like you just had a tape out or have a tape out coming.
Yeah. I mean, it's obviously. Yeah, sorry. The underlying architecture is silicon proven from series 2 and then series 3, and then obviously there's some major substantial changes and improvements in series 4. So yeah, we expect that to be taped out in due course.
Okay, guys. Well, thanks, David, and thanks, Andrew. We'll go to the break now for 10 minutes and be back at the bottom of the hour. So thank you. Talk to you all then.